Hi folks, we are on the third and final video for your Unit 1 Day 3 lesson. Now, we just have one more kind of quick topic to look at, and that's describing direction, kind of north, south, east, west in the real world. And there's two different ways of doing that. On any tests or quizzes, I won't be particular in how you answer. If you give any answer that is correct in either form, that will be fine, but you do have to understand how to interpret it because the bearings or directions may be given in either true bearing or quadrant bearing form. Now this one, the quadrant bearing, is what you've probably seen in grade 10 and 11. I know we do that a lot in the trigonometry units in those courses. And this is where you have an angle that's measured in directions based on how far east or west this is of the north-south line. So you are always going to have an acute angle here, and it's always measured from north or south. So this would be things like south 30 degrees east. So starting pointing towards south, measure 30 degrees to the east, and that's that blue line there. The next one, north 45 degrees west. So starting from north, measure 45 degrees towards the west. And it's important to note that you'll never have something like east 15 degrees south. That never, ever, ever happens. You'll always have to measure from north or south. Okay, so so it always goes starting with the north or south, and then an acute angle and what direction it's pointing towards, the east or the west. The other way of representing bearing is sometimes called true bearing, and this is an angle measured clockwise from north. So this would be, and it's always expressed in 3 digits. It doesn't need to have a direction associated with it because it just kind of defaults to start at north and measure clockwise around in a circle. So this would be 020, so 20 degrees from there. And then the 150 would be again starting from north and going like that. So you could even have much bigger angles. For instance, if you had, say, something that was, let's say like 310 degrees, you would start from north and measure around, all the way around up to somewhere in that quadrant. So you always start from the north and measure in a clockwise direction. So we can represent any of our measurements or directions using these kind of descriptions. There's an example here that has an airplane that's going north at 500 kilometers per hour, and there's an east wind blowing at 150 kilometers per hour, and we want to find the resultant velocity. I just want to kind of look through some of the terminology here. If you have something called an east wind, and this is going to be the same obviously for a west wind or south wind, whatever it is, this means from the east. So this is measuring from east towards west. So the wind's coming from the east going towards the west. Okay. This is the speed of the plane in still air. So if there is no wind at all, that's how fast that plane would be going. And the resultant velocity is the actual real life where and how fast the plane is moving. So resultant will be the actual velocity and the plane's given velocity would be if there was no wind. So that's the plane's velocity without any wind. And in general, this is going to be a common kind of question that we're going to be looking at. We are going to typically take the plane's velocity, add in the wind velocity where it's pushing it, and you will end up getting the resultant velocity. And we could have lots of different combinations of this. You can get questions where you're given a resultant velocity and you want to look backwards and say, how fast must the wind have been blowing, or how fast did the plane fly without the wind, if you were kind of given any two of those three. So just a couple notes, we need to draw a diagram every single time you're doing vector addition. That's really important. And the other thing that I talked about in the previous example, we're asked for velocity, and we know that velocity is a vector quantity, and if you have a vector, you need to give me magnitude and direction. I am not going to say what's the magnitude and direction of the velocity. That's on you. You need to know that velocity is a vector, so you need to give me both parts. Lots of times I will put this on a test and people will draw a great diagram and solve for the magnitude, find the speed of that resultant, but not give me the direction. And it's just sometimes like an easy SOHCAHTOA, but you lose a fair bit of marks because you didn't recognize that that was a vector and you needed to find both pieces. So that's so important. So this is really, really, really important. I would love this to be the year that nobody forgets that part. So I'm going to take a blank page here. We're going to draw ourselves a vector diagram. The plane is heading north at 500 kilometers per hour. So I have my vector P going there, north at 500 kilometers an hour. Now I have an east wind, which again goes from the east towards the west. So I'm going to draw that wind in there. And that is going to give me the resultant velocity. I didn't draw my wind very 90 degree-ish, and that's the resultant. So I've got my plane, my wind, and then the plane is going to get pushed to the side. If the pilot on the plane just steers straight north, the wind is going to push the plane off to the side. So it's going to get pushed towards the west by that wind. Okay. So again, we can kind of go from a vector diagram to a more simplified version. I'm just going to use magnitude of the resultant. This one's a lot easier because we don't actually have any bearings. We don't have like north 30 degrees east or south 20 degrees west or whatever for our wind. We've just got a nice right angle, which is a little bit easier to start. So I'll throw in the numbers there for the magnitude of the wind and the plane. So we can calculate our resultant velocity. We don't even need trig. We've got Pythagorean theorem here. So 500 squared plus 150 squared is the magnitude of the resultant squared. So we get a resultant. Again, you don't need to show me all the steps with the square root and everything. Just show me the equation you used and your final answer. It's 522.02, 2 decimal places accuracy, and that's in kilometers per hour. So that is the tricky part where a lot of people stop and say, oh, I'm done. I found how fast it's going to be going, its resultant speed, but velocity is a vector. You need to have the angle or the direction as well. So I'm going to put in a theta in there and continue on to solve for theta. I'm going to use these two just because I don't want to kind of use the rounded off value in there. So I've got a tan ratio. Tan theta is 150 over 500. And again, you don't need to show me the whole 10 negative 1. I'm trusting you guys to use just kind of one step to show me the formula you used, show me your final answer. So it's 16.70 degrees. Okay. We need to write a statement here because this is the resultant velocity. So you'd say, therefore, the resultant velocity is 522.02 kilometers per hour. And then remember that we can use those square brackets when indicating direction. I'm going to say that's north 16.70 degrees west. So that wind is pushing it about 16.7 degrees off course, and it's actually speeding the plane up a little bit. If there was no wind, they'd just be going 500 kilometers per hour, but with the wind, it's pushing it to go a little bit faster. So that's the kind of thing, like in real life, obviously they have to account for that. And you guys will end up, especially into Unit 2, we're going to have some kind of more complex problems with these where you're working at different angles and different kind of directions as more complex applications to vectors here. And that's it for day 3.